doing for RF circuits or other mismatch concerning circuits as well. And after that, I'll conclude my presentation. Okay, then again, terminology, something is reducing with the, some voltage which is reducing with the temperature, CTAT, some increasing, that is a PTAT. TC is again measure of accuracy over the temperature, and line regulation, again measure of accuracy of that particular reference voltage over the supply voltage, right? And terminology is other terminologies are like a PSNA and MAPV. MAPV generally we won't use in this presentation. That generally just I put that term because if you come across some data sheets and it mentions about the MAPV, you can directly relate that it will with the TC, that is temperature coefficient, right? Power supply noise attenuation is one of the term which I wanted to tell you, is that it is AC performance or AC characterization of voltage reference. There is another AC characterization which I am not talked in this presentation. I will not talk about this also. It's a noise of the voltage reference, because noise is also one of the critical point while designing a voltage reference, particularly if you are designing a voltage reference for a high resolution data converters. Like if you go for a more than 16-bit, which is nowadays it's quite a normal. But yeah, really, if you wanted to go beyond 16-bit resolution data converter and you are using the reference voltage, then definitely you have to think about flicker as well as thermal noise. So that I did not talk about this. So that this is one of the research topic. If anybody wanted to do some survey and research regarding noise of voltage reference for a high resolution data converter, it is open-ended question. Right. Then we have seen some basic concept. We are having VBE1, that is pumping the current into that transistor or a BJT, and it is reducing with the temperature by -2 millivolt per Kelvin slope, right? Then we got a delta VB, right? And we scaled that delta VB by the factor of S, and for value of N is equal to 8. And at a room temperature, if we started calculating the value of S, it will come around 11, right? Then 11 is not a sacrosanct number. This is just, for example, we have taken that. And N is equal to 8 is also not a sacrosanct number. You can have any number of N, considering how much area we are having for a BJT, right? So that if we add VBE1 and S into delta VBE, then it is nothing but we'll get a voltage which we are calling it as V reference, as it is not varying with the temperature at all, right? And we have seen the basic concept. We have converted the voltage into the current, right, and made it flow through the another value of resistor where R3 value is larger than the R2, so that we'll get the amplification factor of S into that particular voltage, that is the VA, right? But we don't want S into VA, we want S into VA minus VB, so that just we put into two batteries opposite to each other, so that we'll get the voltage amplification S into VA minus VB. That I have corrected the current value today. Yesterday I made a mistake, right? But instead of connecting two batteries into back to back each other, I just moved that battery from one branch to another, and nothing has changed, because if you put the KVL, it will be still the same, which you can see in this loop. Everything will be same. It will not change at all, right? But we don't want, again, we don't want S into VA minus VB. We want S into VA minus VB plus VA, so that I put another battery. It's a simple math and circuit additions, right? But unfortunately, we have to replace the batteries with the transistors, and we have replaced that. But here, the transistor current which is flowing through this is VA minus VB divided by R2, and VB1 will not see any current as it is connected to high impedance node of the operational amplifier. So that what we can do is that just copy paste the current and made the same current to flow it through the VBE1 as well, or transistor Q13 as well, so that we'll get the voltage. And this is a complete circuit. Apart from that, we have seen the another approach is that we want S into VA, then just do some non-inverting amplification, but we don't want S into VA, we want S into VA minus VB. And accordingly, we have connected that into the inverting terminal of our operational amplifier, and we derived our circuit. And this circuit is, at the end, it is similar to whatever circuit presented by the Kujiks in way back 1973. And this voltage reference is very, very popular. Nowadays, also many architectures you will find that Kujiks reference they have given. Right, many papers, many circuits, people are using Kujik voltage reference as their part. Right. What are the requirement? Requirement is there are two requirement, as we said, because for evaluating the values, I will get the current which is flowing through the loop having the two values. One is I is equal to 0 and two solutions, in fact, not two values, two solutions, I is equal to 0 and I is equal to delta V by R, right? Why it is coming? Because as we have said is this operational amplifier will be always happy when both the terminals inverting and non-inverting as the same potential, right? As exactly same potential, then it is op amp will not do anything, right? So that as according to our solution, both this inverting and non-inverting terminal will be either connected to 0 or either resting at 0, or it will be resting at 700 millivolt at room temperature. Right? So that there are only two solutions exist for this voltage also, we can say. Right? So that what we have to do is that if while doing the fabrication, we have to make sure that this circuit should awake from its resting position, right? If it is resting at 0 volt, what we have to do is that we have to somehow make sure that one of the op amp terminals should get wiggled somehow. So that for that, designer used the startup circuit, and startup circuit is one of the integral part of a voltage reference, because if there is no startup circuit connected into the connected along with the core band gap based voltage reference design, then there is a possibility that your band gap based voltage reference never fires, so that it's quite mandatory. Right. Then some important sub band gap based voltage, sub 1 volt band gap reference. All right, and this is nothing but a current mode approach, and I have corrected the equation here as well. Generally, if you see this previous circuit, as we have calculated what is a band gap based voltage reference value, and that value was turning around, after plugging the numbers, it was around 1300 millivolt or so at a room temperature, right? Then if V reference itself is a 300 millivolt, I should have a VDD larger than that to make a Q10, Q9, particularly Q10 transistor into the saturation region, right? So that VDD requirement is always higher than the whatever reference voltage we are having for this particular topology which you are seeing on the screen, right? So that if you are working, sorry. If you are working on a 180 nanometer, sorry, 90 nanometer and below, it's very difficult to design or get the conventional band gap based voltage reference, because your VDD itself is limited to 1.1 volt or 1 volt, right? So that it's very difficult to design. One can argue that I'll use the high VT transistors and I can get the higher supply voltage, but that is not a solution actually, because other part of your circuit is working on a 1.1 volt VDD, so that it's not a solution exist as such, right? so that there is a need that somebody should come forward and design a circuit which operates at 1 volt or below that, so that there is a need of scaling the reference voltage itself. Then it is getting scaled by some resistor values, and and for that the Banba used the current mode approach, where he has converted the delta VB related current, delta VB also into the current with respect to that current, and VB also in the form of current. And once VB as well as delta VB got into the current, scaling we can do in terms of a resistor as well, right? Which you can see into the circuit. Converting the voltage into the current and operating that into the current mode itself is considered to be a novel idea, right? So that even though it is quite conventional, but implementation of circuit itself is significantly well, right? So that that is the only reason this circuit is almost used everywhere as a band gap based voltage reference design, almost everywhere, which works on a 1 volt VDD. This circuit, or a derived version of this circuit first came into the picture, right? And after that, all the circuit which you can see working sub 1 volt, it is having similar kind of architecture. Skeleton is almost similar to this. There are some other, what you can say, some other makeups to this circuit people do to improve the performance and all, but skeleton is it's this only. Right. Then another approach we have seen that with this simplest thing is when I1 is equal to I2, then we'll get the current, that is I1 is equal to I2, then that those currents will be p-type current, right? That this is actually, we have just we have written the sentence into the passive voice, we can say, right? So that if we increase the value Vx from 0 to very higher value, then at one initially I1 will be smaller, and after that I2 will be smaller. That means somewhere you will get I1 is equal to I2. Just I wanted to prove this in this slide, and after that we have derived one circuit which we are calling as a p-type generator. But here we have not used the op-amp, but we have used a some transistor or 4 transistor, which by them itself they are following, they are creating the loop gain, which can help us to get the delta VB by R as a p-type current. That itself is a p-type current, right? Again, this circuit also requires the startup circuit. It's not like that this circuit will start by its own. Again, similar thing. This is, again, it is kind of op-amp only, just I put it into the another form, right? So that this circuit also requires the startup circuit that I did not mention in previous or yesterday, right? And again, after p-type, once you get the p-type, it's very easy to convert that into the band gap based voltage reference, right? And if I remove this 2 BJTs, right, then there is a then I have to make sure that this Q19 should be bigger than the Q20, right? Otherwise KVL will not get satisfied, or even though if KVL is getting satisfied, R3 will not have any current as such, right? Because both the VGS will be equal to each other. Right? So that it is important that Q19 should have a K times more, and if K is equal to 4, you will get the famous constant GM bias circuit, right? That I did not mention. When K is equal to 4 only, generally you will get constant GM bias circuit, where this R value should be 1 upon GM of Q20. Right? This information you can get into the Baker or Razavi, Paul Gray, any book with the name of constant GM bias circuit, right? And this is nothing but a VDD independent circuit, means current which is flowing through currents are same in both the branches, and both the currents will be independent of a VDD variation. Mind you, this is again similar to PTAT, derived from PTAT circuit itself, so that current is not again independent of a temperature, it increases with the temperature. So that it is a kind of a CMOS based PTAT current generator, you can say. Right? Because it is nothing but a delta VGS by R. Previously, it was delta VB by R. Nothing has changed. Fine. And one more thing I wanted to tell before leaving this slide is that the connections of 4 transistor, particularly gate source connection, if you reverse that connection, the circuit will not work at all, because feedback action will not be complete. And if you look at closely this loop you analyze, suppose if I'm breaking the loop at Q19, if I'm pulling up this gate voltage of Q19, this will fall down. Drain voltage of Q19 will fall down, right? And accordingly Q20 gate voltage is increased. Means whatever I am feeding back, are you getting? If I am increasing the Q19 voltage, whatever feedback I am getting is again Q20 from the Q20 is again increasing once. Right? If you remember, or if you imagine correctly, increases this will fall, right? And this will increase, right? So that it is nothing but a positive feedback, right? And positive feedback is not always bad unless and until it is not controlled one, right? So that this is the classic and simple example of a positive feedback, which is working perfectly fine. Why it is controlled? Because of this resistance, the positive loop gain is lesser than 1, so that it will not create any problem at all. Right? This circuit, the beta multiplier circuit or constant GM bias circuit itself is a study material to understand a lot of insights and to gain a lot of insights of analog circuits, right? Because they're having a lot of loops and importance of every component associated with, so that itself is a study part. Remember, don't use be cautious while designing a band gap based voltage reference. Don't use any fancy op amps. Use only simple op amp, right? And preferably single stage op amp, because rest of the part will give you multi-stage or 2-stage operational amplifier kind of behavior, so that you don't have to worry much. One more interesting fact, it might be already known to you, that is how much diode smaller or bigger, it doesn't matter. In a small signal, every diode will give exactly same small signal resistance or impedance, you can say. And there are 2 loops into the band gap based voltage reference. One is a positive loop and second one is a positive feedback loop, and second one is a negative feedback loop. But positive feedback loop is weaker than the negative feedback, so that band gap based voltage reference functions well or as designed. Okay. Now coming back to the optimization, we are having reference voltage. Again, we are getting back to the fundamental equation, that is S into delta VB plus VB1, right? Then S we can replace by some resistor ratio, that is I have mentioned here as R2 by R1, and VT ln N, that is nothing but a delta VB plus VB1, right? This is S is R2 by R1, delta VB is nothing but VT ln N, and is nothing but a ratio between these 2 transistors. We have studied multiple times from yesterday to today, right? Then if I take the dV by dt, right, then what it should be 0, right? But if I take the derivative of first term also, then it is nothing but R2 by R1. VT's derivative is nothing but K by Q, and ln N is again a constant number, so that it is K by Q minus 2 milli. Right? Why this slide is important is if somehow by some mean somebody says that okay, you cannot increase the scaling factor quite significantly, right? When somebody says that you cannot have a s is equal to 11, you have to reduce it to suppose 11 by 2, right? Then what you have to do, you because this we cannot do anything with the 2 millivolt, 2 milli number, right? Because it is a derivative of or slope of VB1, which is with respect to temperature. So that if somebody says that you cannot increase or you cannot use the high value of R2 by R1 ratio, then there is only thing which limited or which is in designer's hand is n, right? Means you have to have increased the BJ, one of the BJT, right? So that you can satisfy the slope requirement, right? Then only you can cancel it by the exactly same amount. Okay. Another thing which you can consider is that, okay, constraints are same. I cannot use the increase the R2 by R1, right? I cannot do anything by K by Q. It's a constant. Then if you are not allowed to increase the n as well, then what you can do, you can change the ratio of I2 by I1. And what it is I2 by I1? I2 by I1 is nothing but these two currents. Previously, we said that you cannot, it is not, you cannot change the current which is flowing through both the transistors, but unfortunately, it is not true at all. You can change the value of I1 and I2 to compromise the value of n. At the end slope, right? But generally it is not preferred because it creates a problem of the systematic mismatch between these two transistors, right? So that it is because the moment you are changing the current, you are changing a lot of the things in a small signal domain as well, right? You are changing a small signal resistance, right? That is primary concern while selecting the loop. But yeah, considering all those points, mm, uh, it is advisable to have a I1 is equal to I2, right? But if there are concerns between scaling as well as concerns about the area increment of a BJT, right? Then there is no way designer can go there. He or she has to scale the value of I2 or I1, right? So that these are some parameters. There are very limited parameters for optimizing this circuit, right? Now we'll go back to what are the error sources, or we'll see the what are the error sources in voltage references. First thing first, that is offset. Offset of op amp is a benign thing. You cannot have, if somebody is claiming that my operational amplifier is having a zero offset, then that means you can straight away say that he is lying, right? Then as offset is benign, then what we can do to reduce the effect of the offset on a final reference voltage, right? Here plus sign is missing, but yeah, we can do that. Yeah. Then again, what is the effect of offset on a reference voltage? What we can say is that reference voltage is nothing but, again, this R2 by R1. You have to solve this KVL, right? It's not so difficult nowadays. And extra term you are getting over here is nothing but R2 by R1 into offset voltage, right? Means here, if my if I keep the previous value of R2 by R1, that is 11, that is S value, is 11, and suppose VOS is 10 millivolt. 10 millivolt is not a number uh, which is something exaggerated kind of thing, right? It's a 10 millivolt offset it is very much possible in any technology node, even though if you design it with a lot of care. right? So that uh, considering S value is equal to 11 and offset value is around 10 millivolt, then 10 millivolt into 11, it is nothing but 110 millivolt. It's a huge value, right? Means you are designing your circuit of a voltage reference for 1200 millivolt and you are getting 1310 millivolt, right? It's not acceptable at all, right? And this problem will be much more severe when you come for a sub 1 volt base band gap based voltage reference. Means you are designing for 400 millivolt as a reference voltage, but you are getting 500 millivolt as a reference voltage. This is around 25% uh, extra you are getting, right? It is not at all mm, uh, not at all acceptable into any form of the circuit domain, right? Then how to tackle those problems? There are multiple ways to tackle those problems. Just one way is that whatever optimization what we have seen, right? Uh, you can reduce the value of R2 and R2 divided by R1, means reduce the value of S1. Then we know that how we can reduce the value of S. For reducing the value of S or this R2 by R1, either you have to increase the value of I2 by I1 or ratio between I2 by I1, or you have to increase the area of this transistor, right? So that these are some ways where uh, we can increase the value of R2 by R1 to minimize the offset effect, right? This is a one solution. Other solutions are quite complicated. People use the chopping technique because chopping is generally preferred to avoid the offset. Means chopping means what actually we are having the operational amplifier along with the offset, and we chop the signal to the higher frequency. At the same time, uh, we chop the signal at the higher frequency and one second. Yeah, and amplify the offset and chopped frequency, amplify it further, and after that again dechop it. And while dechopping, offset will move now to the higher frequency, and uh, input signal will come to the lower frequency, and then put your low pass filter and done, right? So that is one way we can do the chopping. But chopping generally, many people have done this, but chopping is generally is not preferred for this kind of circuit because chopping will create another issues like a spikes of that particular chopping frequency, so that generally it is avoidable. Apart from that, if I'm using the low pass filter, right, it is having its own temperature dependency, uh, so that it is not advisable to use the chopping into this. But you can find some paper where people talk about the uh, op amp, chopped op amp for band gap based voltage reference. There are some other techniques, is that uh, you can have something like this kind of configuration. And if you uh, look at the equation, what you can do is here you are getting the n square value. So that coming back to the previous equation, if you remember the previous equation, if n is quite large, I can reduce the value of R2 by R1. And same thing has happened over here. Because of this architecture, instead of n, we are getting the n square. As there is an n square, you can reduce the value of R2 by R1 by some amount. You cannot increase by significant amount, because you can say that there is exponential dependency between the logarithmic dependency between the n, right? So that even though if you increase the n double, you will not find a significant decrement into the scaling factor. Apart from that, what fundamental problem with this kind of architecture is that here you are getting the 700 millivolt. Here you are getting the 1400 millivolt, right? And after that, again, you are having some voltage above that. So that mm, here you will get something delta VB. So that overall this circuit will not work at all at uh, 1000 at sub 1 volt voltage reference, right? Anyhow, because you require at a stretch something like a 1400 millivolt, I mean 700 millivolt. Immediately we have increased just by putting one of the transistor at the bottom, right? So that you are increasing the area by the factor of n. Apart from that, you increase the VDD requirement by the 700 millivolt, right? And this problem is quite significant if your circuit is operating at the lower temperature ranges, right? At room temperature, it is 700 millivolt, right? But if you go for a temperature below room temperature, like a 10 degrees Celsius or something like that, your VB is no longer 700 millivolt. It will be 800 to 900 millivolt. So that this kind of circuits are really, people don't prefer below 180 nanometer technology. At 180 nanometer technology also, it can operate only at the room temperature and above. Below it is very, very difficult, right? So that you are sacrificing the area just to tackle the offset, so that from here you can figure it out how much uh, important offset is. Now, another technique to reduce the offset is similarly, you have to increase your area, right? You have to have increased your area, and that is the only solution people may be figuring out. If you are here increasing the area by n, and offset is getting reduced by the factor of half, right? Okay. What is the difference between previous and this? Here it is n square is there, so that you can scale R2 by R1. And here still n is there, and you can scale only by half. Means here in this architecture, it is fixed that your offset is reduced by the half. In previous architecture, you are having some luxury that you can select the value of n, and depending upon that, you can scale the value of R, right? And whatever the disadvantages with the previous architecture, similar disadvantages with this architecture as well, right? Uh, so that we are not doing any better in this architecture also, right? In terms of area and area and what I can say, area and VDD or something. That means area and supply voltage. But this, if anybody asks me which architecture you will go with, and then I'll go with the, the architecture which you are seeing into screen, right? Means I am sacrificing my area, I am sacrificing my supply voltage, and here also same thing, sacrificing my area and supply voltage, but at least I'm saving some power in this, right? Here we are having only three branches. Here I have to have 5 branches, so that at least I can save some power to just again to get rid of or reduce the offset value. Another error source which is also quite prominent is a PSRR, right? Why it is a PSRR is important, because PSRR generally is important when your reference voltage is providing reference to the high frequency circuits, right? Because we have seen in a PSNA that it is your AC attenuation will start reducing as the frequency increases, right? If you remember correctly, yeah, here attenuation will start increasing as your frequency increases, right? As attenuation will start reducing as your frequency increases, so that So that this is one of the important parameter when you are designing your reference voltage for a high frequency circuits, right? Then what is the solution? Solution was it was simple solution. It was not so difficult. This is one of the solution. Here just this circuit is it is not exactly this circuit, right? This circuit is different than this circuit. Here it is a PMOS based operational amplifier. But one thing you have to be make a point that current source transistor is driven by the operational amplifier's output. That is important thing, because if VDD goes up at the higher frequency, if VDD goes up, the source drain of M4 also goes up. Accordingly, output also goes up. Output of the op amp also goes up, right? And it is connected to M1 transistors gate, right? So that if VDD increases, if we study the feedback correctly in proper direction, then you can say that VGS also is increasing. Means at high frequency, your VGS is getting tracked, right? So that, and it is also linked with the reference voltage branch, so that your VGS, as your source voltage is increasing, your gate voltage is also increasing by the same amount, so that net current which is flowing through a transistor will not change, right? So that tracking help us to reduce the or improve the PSRR response, right? Some other techniques are also there. Just I'll orally tell you that for at the end, what we have to do is that if there is some variations onto the supply voltage, it should not be leaked to the reference voltage. Then one solution is this by tracking, and another solution is it's providing shielding, right? Means you can connect some cascade arrangement along with this circuit, right? Means here you can put another branch on top of this transistor, right? Another layer of a transistor, so that, and some circuit arrangements, right? So that you can shield the VDD along with from the reference voltage, right? So that it will not directly leak into reference voltage output, right? So that this is one of the error source. Another error source is current mismatch, and this is again, it's a benign. It whatever you do, there will be a offset, there will be a mismatch, right? So that it's only a circuit circuit designer skills, how he's designing those circuits, and layout designer skills further on, right? And if you see this circuit, there is a current mismatch. If current flowing through the middle branch is I2, then current flowing through the left hand branch is nothing but I3 is equal to I2 into 1 plus EM2. EM2 is nothing but a ratio. It is lying between 0 to 1, right? 0 means no mismatch, and 1 means we can say highest mismatch in that sense. If means relative mismatch, we can say. If it is EM is equal to 1, it's the largest number. When I1 is equal to I2, then here it is a EM1 mismatch, we can say, and here it is a EM2 mismatch. Then considering these two mismatches, right, then which mismatch is much more concerning, that we have to figure it out. After solving this equation, equations are quite small, so they're quite easy, so that I did not put into this slide, and it may look like a clutter as well, so that is also not the purpose of this workshop, right? So that on this is well, delta VREF current mode mismatch is it's dominated by the first term, that is EM2 term, right? EM1 term is also there, but it is having less dominance because it is not getting multiplied by the factor of ln n, right? Then what is a solution. The solution is again similar, that you have to reduce the value of R2 by R1, right? You can scale the value of R2 by R1 by some factor, then you can have a lesser mismatch, lesser deviation from its mean value of reference voltage. Sorry, right? But from here, you can easily say that EM2 is contributing larger to the variation as compared to the EM1, right? And factor is only ln of n. Okay. Another thing which causing the mismatch is systematic mismatch, and this systematic mismatch is no longer acceptable in any kind of design where mismatch is a concern, right? Why this systematic mismatch is coming? You can say that all the M1, M2, M3 source is connected to one potential, or exactly same potential for three. Gate is also connected to same potential for three. Then why mismatch is causing? Because VDSs are not same, right? At room temperature, I'm getting reference voltage at 1.200 millivolt, as it is a conventional, but VA and VB at 700 millivolt, right? So there is a difference of 500 millivolt in the VDS of these two transistors, M3 and M1, M2, right? So that definitely it is causing a systematic mismatch. And so how to avoid this systematic mismatch? Why systematic mismatch is coming, that is clear, because VDS are not same. So make the VDS same, right? So that I put some value of R3 and R4, so that I'll make sure that here also 1.200 millivolt, here also 1.200 millivolt, on its VRF reference voltage is 1.200 millivolt, 1200 millivolt, right? So that by just connecting two resistors, R3 and R4, I can get rid of systematic mismatch, right? Again, fundamental rule of analog IC, nothing comes for free. You have to sacrifice the area to get the to avoid the simple systematic mismatch also. Other thing is just nothing but it is a similar way. They are putting some cascode. Cascode is also one of the way you can reduce the offset. It's nothing but a shielding, right? Means other transistor will see, means top transistor, by this mechanism, top transistor will see the same VGS and VDS. That is also one of the thing. But again, we have to increase. Instead of putting resistor, we are putting one transistor, one row of transistor. That's all. Nothing else with this kind of architecture. Another error source, that is a base resistance. Whenever I'm using this parasitic BJTs, right? The base is nothing but a NVEL, right? Base is nothing but an NVEL, and NVEL is not so, what you can say, not so conductive doping concentration that is associated with that well, right? So that base also will be having its own resistance, and because of the base resistance, we are getting some delta variations into the reference voltage, right? And again, if we look at closely, the R1, R2 by R1 factor also comes into the picture, right? Means if because of the base resistance also creating the variations into the reference voltage, but by reducing the scaling factor, that is R2 by R1, you can reduce it, right? Means from this you can gauge that scaling factor is how much important it is. It's either you have to play with the R2 by R1 ratio as a ratio, or you can play with the N, or you can play with the current which is flowing through the BJT, right? These are some things which I wanted to tell you. But apart from that, how to get rid of this error? We cannot get rid of this error or base resistance error completely. Just we can have some extra stamping to well, that is the one way we can reduce the value of RB1, 2, and RB3. Right? Extra damping means just make it that put extra connections to well in the BJT. Right? So that by that way, you can reduce the base resistance, and as you reduce the base resistance, then definitely you can reduce the spread. So that this is general technique people do. They'll connect more connections to the base, so that it will be having the lesser resistance. And then there are a lot of error sources, but I have taken few only. Other error source is that whatever value you have selected, it is not exactly same what you have done in a simulation, right? Means I have selected 11K and 1K, right? Then 11K can be different than 11K, which is getting fabricated, is different than whatever you have simulated, right? So that then one can argue that R1 also may be different than whatever R1 you have simulated, right, after fabrication. But for modeling, you can model into single one, right? So that you don't have to again model into R1. Otherwise, it is double work, results will be similar. So how much variation it will cause? Again, same thing. Either you have to reduce the value of R2 by R1 scaling factor, or reduce the value of N. We can do both if we change the ratio of currents, right? R2 and R1, which is not good because you lie into the mismatch related issues. But what is most important that you have to think of and you have to proceed further, right? Is everything about the specification and designer skills. There are now how to tackle with this kind of thing. There are a lot of error sources which we have seen, and tackling each and every error source is very, very difficult, so that people figured out some smart way to tackle this. That is a trimming technique. Means here, if there is a mismatch, you can trim this. If you wanted to change the scaling factor, you can trim this, right? And if you want to change the N, you can trim this, right? This is nothing but a trimming. And this, whatever it is connected as, it is considered to be a fuse, right? You can burn those fuse and you can release the resistor into the circuit. Otherwise, it is shorted. All right. And these circuits are also quite common in, it is not very common into the industry because in SOC it is not at all common. If you are having individual reference IC or individual LDO IC where you are using this band gap based voltage reference, then it is quite common. And if you are having the bigger circuit where band gap is one of the part of that circuit, then generally people don't go for a trimming, because once you said that my circuit band gap based voltage reference need trimming, then you have to trim each and every IC, right? And it consumes a lot of time, lot of energy, lot of power, right? It's human power is also very much involved, because manually everybody has to do that for blowing the fuses, right? So that if there is a time constraint, or if there is no time constraint as such, and if there is an extreme need to trim the reference voltage, then only people go with trimming. Otherwise they'll not go. And if they're not going with the trimming, then they'll mention the band, right? My reference voltages will vary from this much voltage to this much voltage, or percentage, That again, coming back to the first slide, temperature coefficient, right, which I was talking about. Then they'll say that temperature coefficient best and worst case, and uh, depending upon the application, people select that. Okay, before going to curvature correction, I'll take a, I'll ask you if you have any doubts, right? Because we're having one half an hour more. Right. Is there any doubt or concerns or queries?
Any questions from the participants?
Hello, sir.
Yeah, tell me.
Hello.
Yeah, yeah,
Sir,
tell me.
so can you tell me, sir, what is the use of dummy transistors which we are using in the layout?
Oh, okay. I'll come to that point once I'll reach to that layout part.
Oh,
I
okay,
think it will take 15 minutes to reach that point.
okay.
Okay. Any other thing?
Sir, you said that we can avoid that mismatch, systematic mismatch by
Mm-hmm.
cascoding. So, cascoding,
Okay.
does it mean we are shielding the power supply, power line?
1 second. I'll go to that slide, right? Yeah, right.
Oh, yes, this one. So initially we were using resistors to adjust that VDS because VDS is different for all three lines.
Right, right.
So you said that instead of resistor, because if we are using resistor, we need a more area, more space on
Mm-hmm.
chip. So we can go for cascoding. So cascoding means again we are here adjusting the VDS only, changing the VDS, or we are shielding supply.
No, actually, here what we are making sure is that top transistor is now our governing power, right? So that
Okay.
top transistor will try to make it exactly matched with each other, right? So that there will be no mismatch, current mismatch. But again, this is not a fair solution as you pointed out. It will give better PSRR response, but
Hmm.
systematic mismatch it will not help to the extent. It will definitely it will help, but it will not help to the extent, right?
Okay. Okay.
Because still there is a difference between reference voltage and this voltage, right? Right. But only thing is that it has made sure that this three transistor will take care of that. But I don't know. I have not simulated this circuit. Uh, Anybody else? I think there are no more questions. I'll check.
Sir, one more question, the last.
Yeah, yeah. Please
Sir,
go ahead.
you in the last slide you said trimming. We are using trimming for removal of error source.
Mhm.
There you have used fuse. So how this fuse is fabricated in chip?
Oh, okay. Fuses are fabricated with some, actually, it is, uh, yeah, 1 second. Yeah, here. This is generally people are not preferred. Why it is not preferred, I will tell you. Because every fuse will be having two pads associated with each other, right? And and by that way, the fuses are connected. Means two pads with some. I don't uh, remember exactly. There is, I think, some small line which is or some small conducting wire which is flowing through that, and when you wanted to fuse them up, we'll give some higher voltage so that that line is getting blown out, right?
Okay.
So that it is not preferred in a SOC, as I said, because for trimming you have to provide the pads, which is not generally people don't. prefer those kind of thing. Pad is kind of a huge thing. So that just for a trimming your reference voltage, nobody is willing to give their pads for designing a fuse, right? But if it is a standalone reference voltage, then uh, definitely you are very much worried about your accuracy, so that you can go with you can sacrifice your pad area in terms of a pad, and you can use some fusing technique.
Okay. So standalone means only if suppose if there is only one IC of band gap reference only. That's it.
Right, right,
That
right,
is
right.
the
That
okay.
is I'm talking about.
Okay. So when we
Uh,
say SOC means there are multiple circuits are on one chip.
yeah, right,
So
right.
there may be a band gap reference also op amp also A to D
Yeah,
converter
many
all.
things like
Okay.
low noise operational amplifier, low
Yes.
noise chopping circuits, or after that data
Yes.
converter, after it some digital processing DSP part or something like that.
Okay. So there we can't go for trimming. This is only useful for the standalone IC of band gap
Which,
reference.
according to my analogy, yeah, it is true.
Okay. Okay. Thanks.
Yeah. Okay, I think we'll move to the presentation mode. Yeah, curvature correction. As I said before, this VB, which we are talking about, minus 2 millivolt per Kelvin slope, it is not true. We are having some slope which is reducing with the temperature. It is having some physics involved into that. For that, you can read. I read Paul Gray book, so that if you want, you can read that as well. Some other papers as well, but Paul Gray will give the nice understanding about this. And this curvature is something like, means what this curvature means, if as temperature increases, your slope will be much steeper and steeper. That it means, right? And because of that, you are getting some curved thing. And now at delta VB, slope will be always straight. That is Vt ln n, right? If you take the derivative, it is nothing but k by q into ln of n. So that is just number, right? So that slope of delta VB is always linear, where slope of slope of VB is always non-linear. So that because of that, you are getting the curvature into the reference voltage, right? And this will limit your accuracy, right? Then what people are doing is that I'll not get into a detail, just I'm giving you overview what people are doing. They are having some extra circuitry where they are putting this nonlinear current into the circuit, and at the end, that current they are adding together and flowing to the R2 and converting to the current into the voltage. And here you can say that previously it was like this curve, right? And now it is reduced to this. Means it is kind of folding back that upper peak, so that you can improve your accuracy at least by the factor of half or something. It depends, right? So where you're, as I said, that when you are using a 16-bit or 18-bit ADC or 20-bit ADC, then people go for a higher order corrected voltage reference if you are using the voltage reference as for generating the reference, right? There are some other things, which is this is exactly the what parasitic BJT look like. Emitter is P plus. Base is N plus and collector is P plus. The collector P plus is nothing but a substrate, right? And emitter P plus is nothing but a P plus area. That is that we can use it for a drain or source for a PMOS, right? And N plus is again same thing. This N plus region we can use it, or generally it is used for a drain or source of NMOS, right? Uh, Now we'll look at the doping concentration. P plus doping concentration is around 10 raised to uh, plus 19. Actually, it is 9 has come down. Okay. And N well concentration is 10 raised to 16. And P substrate concentration is around 10 raised to 15, right? Why these numbers are quite important are having the beta effect. Now, with this uh, with this graph, you can see that your beta is also increases with the temperature. And why it is happening? Because of the VGE and VGB divided by VT. This term is coming to the picture, right? And this was not the case if you are having the conventional BGT. Your beta does not vary with the temperature, significantly with the temperature at all, as I can put it correct way. Uh, why it is happening in this parasitic BJT? It is happening because of the number of numbers which is associated with the concentration, right? You can see that 10 raised to 19, 10 raised to 16, these are the quite a huge number. And once you cross the 10 raised to 15 or 10 raised to 16 kind of concentration level into a semiconductor, then you will come across the phenomena which is called as a band gap narrowing, right? And band gap narrowing is nothing but in suppose it's silicon. If silicon is heavily doped with something, its band gap will not be 1.1 electron volt. It will be little bit lesser than that. And similar thing is happening over here. As emitter is heavily doped, right? As emitter is heavily doped, its band gap is little bit lower than the base band gap, right? This is 10 raised to 15 and 10 raised to, 10 raised to 16 and 10 raised to 19, right? So that you will find that there is a difference between the band gap, even though both are made up of a silicon, right? But as it is doped with the very, very heavy concentration, you can find there is a effect of band gap narrowing, and it is causing the beta to vary with the temperature. And that exact phenomena, we have tapped it over here. And first time we have published some results is a multiplicative based voltage reference. Here we are having VT ln N2 by N1, which is increasing by the increasing with the temperature, and some beta and resistor values, which is reducing with the temperature, right? And this is VT ln N. We got something like this, and some beta and resistive values, something which is reducing with the temperature, and we have multiplied it. This is the first kind of multiplicative based band gap based voltage reference. I think we have published in 2014, I guess, right? Why it is important is that we don't have to do some additional circuitry, right? And still we can get the curvature corrected output reference voltage, right? That is the beauty of this circuit. And these results are, again, as you can see that these are the measured results, so that whatever we are seeing is having the proof of a silicon. With the interest of time, I have to run a little. Another thing, again, similar kind of curvature correction architecture was presented by the CAR in JSSC 2016. It is similar thing. They are having he has used two reference voltage circuits, and one is a adder in between, right? Why it is happening? Why we are getting the curvature correction in sub-circuit 2? Because of that, I'll get the inverted U, and sub-circuit 1, because of this configuration, I'll get the here I'll get the U, and here I'll get the inverted U, right? And once is a U and second was the inverted U. If we add it together, I'll get the averages. It should be constant line, right? Are you getting? One is a U and second was the inverted U. If you add it together, you will get the principally it should be straight line, but it will not be straight line, right? So that you can, definitely it is better than the conventional band gap based voltage reference. But again, you have to have a double the power to get that accuracy. Another thing which we have published is MOSFET based voltage reference, where what we have done is that we have used the different W's to create that, to study the dependency of coefficient eta, right? Eta factor you can see into the transistor's equation when transistor is current equation of a transistor when it is operating into the subthreshold, and it is having the dependency on a temperature, and we have tried to tap that we got this circuit. I'll not get into a detail, and that you can read this paper so that you can get into what we have done exactly. And this is a reference voltage, which we can see that is varying from, I think, minus 35, I guess, minus 35 to 125 degrees Celsius. And we are getting the curvature corrected response. Another one is a line regulation. Last thing, which I wanted to discuss is the layout technique, right? And as somebody has figured out, is that I think Miss Madhuri, I guess, figured out that why dummy is required, right? Then here is the ratio of Q1, Q2, and Q3. Means we are having the three kind of transistor where Q1 I have opted as a 4, Q3 I have opted as a 4, and Q2 I have opted as a some number that is nothing but that highest value is generally selected as a n square minus 1. N square minus 1 means or n square minus ratio of other transistor, I mean number of other transistor. Why that n is coming? Because if I am having that number over here, then every time that n should be what you can say odd number, right? N should be always odd number, right? If it is, because why it is odd? Because if I say this is 1, 2, 3, 4, 5, 6, 7, 8, 9, then I can get 9 over here. I can get 9 over here. If it is even, then I cannot get a square out of that, right? So that it is always good to have wider transistor where n is a odd number, right? If it is an odd number, then doesn't matter. You have to put the extra dummies into that, but unnecessary why to waste the area? Better to have a odd number of n. And I think you know that what I am talking about. N is that bigger transistor area I'm talking about, right? And this is Q3 and Q1. We have selected 4, 4. This is 1, 2, 3, 4, and gray is Q3 is 1, 2, 3, 4. And here the one space was remaining, so that I put the dummy. Dummy transistor generally we put because because when there is a process variations, right? Then if I keep this empty, when I keep this empty, then what will happen? Okay. Okay, in this case, I don't know how to explain this, but yeah, generally why dummy has put is that if I'm fabricating the transistor, both the transistors should see as similar kind of a environment while doing the fabrication, right? So that if I don't, suppose I'll give the example. If this is one of the transistor, right, then this transistor will not behave, this transistor will not behave same as this transistor, right? Are you getting? Why? Because this transistor is surrounded by other 8 transistor, right? But this corner transistor is only surrounded by the 3 transistor, right? And when you do the fabrication process, this transistor characteristics will be somewhat different compared to this transistor characteristics, right? So that if your circuit is very, very sensitive to process variation, then it is definitely advisable to put some other transistor, which will make sure that this transistor will look like this transistor, right? Means this transistor will also feel that I am in the same environment as a just transistor diagonally opposite to that, right? I think this was because of this precise reason people put the dummy. But again, in dummy, while putting the dummy, again, it is you have to tell the layout engineer if your circuit designer is not doing doing this dummy thing, or in fact opposite, layout designer will tell you that he has put that dummy into that, so that you have to add that into the circuit. Otherwise uh, otherwise your LVS will not get clear. So that while putting dummy is important thing, but again, um, passing the information of a dummy, putting the dummy has to be nicely passed to the circuit designer engineer as well, right? So that there will not be any LVS issues. Right? So that here what reference book I have used is a CMOS voltage reference for analytical and practical perspective. Major content for this presentation I have taken from this, so that many times I have not put the reference below the circuit diagram, but if you find out this book, you can find the reference in this book itself, right? So that you can go back and study those circuits into the deep. Finally, conclusion, voltage reference is one of the important design skill, which gives a lot of understanding about the DC as well as small signal analysis in simpler way, right? And last and not the least, it's analog is fun, so that